More than half of Earth's entire weight is iron, 32% of the planet's mass. Earth's core is a gigantic ball of molten iron the size of the moon. But iron rules on the surface too. Every second, humanity produces 60 tons of steel, 2 billion tons per year. That's more than all other metals combined. 95% of all metal used by civilization is iron and steel. Without iron, there'd be no skyscrapers, bridges, ships, cars, or trains. How do fiery rivers of molten metal at 3,600 degrees emerge from red ore in city-sized quarries? You'll see explosions in quarries, blast furnaces as tall as 30-story buildings, converters where oxygen turns pig iron into steel in minutes, and rolling mills where 1,000-ton slabs get rolled into paper-thin sheets. Watch to the end. The finale shows why iron holds the world together. This is the story of the metal that built civilization. The Lebedensky quarry in Russia is one of the planet's largest iron ore quarries. Depth, nearly 2,000 feet. Width, 3 miles. From the edge, you can't see the bottom. A gigantic wound in the earth from which 100,000 tons of iron ore are extracted daily. Excavators as tall as 10-story buildings scoop rock with buckets holding 1,800 cubic feet. One bucket is like a small house. Dump trucks with 360-ton capacity haul ore up the spiral road. Wheels taller than a person. But before loading the ore, it needs to be blasted. Drilling rigs create holes 65 feet deep. Tons of ammonium nitrate explosive are packed into these holes. The explosion? Earth trembles. A wall of rock tall as a skyscraper crashes down. A dust cloud rises 3,000 feet. After the dust settles, excavators begin work. The ore is reddish-brown, sometimes almost black. Magnetite and hematite, iron oxides. Iron content ranges from 30 to 60%. The rest is waste rock. The ore goes to a processing plant. Massive cone crushers grind bus-sized chunks. The noise can be heard for miles. Ore gets crushed to fist size, then to gravel, then smaller. It enters ball mills, steel drums 20 feet in diameter, 33 feet long. Inside are hundreds of tons of steel balls. The drum rotates, balls drop, grinding ore into fine powder. After 8 hours of grinding, you get reddish-brown dust. It's mixed with water, creating pulp, liquid slurry. This slurry passes through magnetic separators. Magnetite sticks to magnetic drums. Waste rock washes away. The concentrate contains 65 to 70% iron. From this, they make pellets, granules the size of walnuts. Wet concentrate gets rolled into balls on special drums, then fired at 2,400 degrees Fahrenheit. Pellets harden, becoming rock solid. These pellets are raw material for blast furnaces. Each plant produces millions of tons of pellets yearly. They're loaded onto trains and shipped to steel mills. A blast furnace is a steel tower 330 feet tall, 46 feet in diameter. 30 stories of pure metal and fire. Lined inside with 3-foot-thick fireproof brick. Internal volume, 176,000 cubic feet. Iron ore pellets, coke, and fluxes like limestone or dolomite are loaded from the top, in layers, like a layered cake. Several hundred tons at a time. From below, through tuyères, openings in the walls, hot air is blown in. Air temperature, 2,200 degrees Fahrenheit. Pressure, 4 atmospheres. Coke ignites. Temperature in the furnace's lower section reaches 3,600 degrees Fahrenheit. Pellets slowly descend, heating up. Different reactions occur at different heights. First, moisture leaves the ore. Then, at 930 degrees, iron oxide reduction begins. Carbon from coke strips away oxygen. At 1800 degrees, ore becomes spongy iron. At 2700 degrees, iron melts. Drops of molten metal flow down. At the furnace bottom, molten pig iron accumulates, an iron alloy with 4% carbon. Pig iron temperature at the furnace bottom is 2700 degrees Fahrenheit. It glows blindingly white with an orange tint. Pig iron is denser than slag, so it stays at the bottom. Slag, molten impurities and fluxes, floats on top. Every 4 hours, they open the tap hole, an opening in the furnace's sidewall. Pig iron tapping is a fire show. A stream of molten metal flows down channels. Sparks fly dozens of feet. The brightness requires dark glasses to watch. Pig iron flows into massive ladles on railroad cars. One ladle holds 300 tons. It's a locomotive made of molten metal. The ladle gets covered to prevent cooling and shipped to the steelmaking shop. One blast furnace operates continuously for years. Stopping is catastrophic. Metal would solidify inside. The furnace produces 10,000 tons of pig iron daily. That's like 100 railroad cars. Major steel mills have 10 to 15 blast furnaces. But pig iron isn't steel yet. It's brittle due to high carbon content. Steel is needed, an alloy with less than 2% carbon. Pig iron gets poured into a converter, a massive pear-shaped vessel 33 feet tall, lined with fireproof brick. It holds 350 tons of molten metal. The converter tilts, pig iron pours in, steel scrap is added for cooling. The converter returns to vertical position. An oxygen lance, a tube 20 inches in diameter, lowers from above. Oxygen flow begins. A jet of pure oxygen at 150 pounds per square inch pressure strikes the molten metal. Violent reaction begins. Oxygen oxidizes carbon, silicon, manganese, impurities in pig iron. These exothermic reactions release enormous heat. Temperature rockets to 3,200 degrees Fahrenheit. Metal boils and churns. Flame tongues several feet high shoot from the converter mouth. Sparks and molten drops fly everywhere. The blowing process takes 20 minutes. In this time, 350 tons of pig iron become steel. Carbon burns down to 1% or less. The converter tilts, steel pours into a ladle. The molten metal glows blindingly white at 2,900 degrees Fahrenheit. Alloying elements get added to the ladle. Manganese, chromium, nickel, molybdenum, depending on the steel grade needed. They mix it by blowing argon through. Then steel gets cast. There are two methods. First, continuous casting. Molten metal pours into a crystallizer, a water-cooled copper mold. Below, a solidifying blank emerges, a slab 8 inches thick, 6.5 feet wide. It glows red. Surface temperature around 1,800 degrees Fahrenheit. Gas cutters slice the slab into 33-foot lengths. One slab weighs 25 tons. Second method, casting into ingot molds. Steel forms. This creates ingots up to 50 tons. These ingots and slabs are semi-finished products. They go to rolling mills. There begins the final transformation, turning thick blanks into thin sheets, rails, or beams. Slabs heat in reheating furnaces to 2,200 degrees Fahrenheit, red hot. Then they go to the rolling mill. It's a line of dozens of rolls. Steel cylinders 3 feet in diameter weighing dozens of tons. Rolls rotate toward each other. The red-hot slab enters between rolls. They squeeze and roll it. The slab gets thinner and longer. It passes through the next pair of rolls. Even thinner. Dozens of times. An 8-inch thick slab becomes a sheet 1 to 2 millimeters thick. Length grows from 33 feet to over half a mile. Rolling speed on finishing mills reaches 50 miles per hour. Red-hot steel ribbon flies through the mill, sparks flying everywhere. Temperature drops to 1,400 degrees Fahrenheit, metal darkens. The strip cools with water, winds into giant coils weighing 20 to 30 tons. This is hot-rolled steel. the foundation for car bodies, appliance housings, building structures. Global steel production is 2 billion tons yearly. China produces over 1 billion tons, half the world's output. India, Japan, the US, Russia are other major producers. Steel is infrastructure's backbone. 95% of metal structures are steel, from skyscrapers to tin cans, from tankers to paper clips. Iron and steel are civilization's skeleton. Iron is the oldest metal after copper and bronze. The Iron Age began 3,000 years ago. First, iron came from meteorites, ready-made metal fallen from the sky. Egyptian pharaoh Tutankhamun was buried with a meteorite iron dagger. Smelting iron from ore was learned by Hittites in Asia Minor around 1200 BC. They kept the secret for centuries, but technology spread. Iron weapons were stronger than bronze. Iron plows worked soil better than wooden ones. Civilizations with iron defeated civilizations without iron. Medieval times, iron was made in small furnaces. The Industrial Revolution began with blast furnace invention in the 18th century. Early furnaces used charcoal. Later, they switched to coke from coal. The 19th century brought the converter process, rapid pig iron to steel conversion. Bessemer, Martin, Thomas, names that changed the world. The 20th century was steel century. Skyscrapers, bridges, ships, automobiles. Without steel, there'd be no modern world. And so, traveling from explosions in 2,000-foot-deep quarries through giant crushers and magnetic separators, through 300-foot-tall blast furnaces at 3,600 degrees and converters where oxygen burns out carbon in 20 minutes, through rolling mills where 8-inch slabs become millimeter-thin sheets, steel emerges, the metal that built civilization. 2 billion tons per year, 60 tons every second. The metal everything around us is made from. Every skyscraper, every bridge, every car, every ship. It's iron, mined from red ore, remelted in fire, rolled into sheets. More than half of Earth's weight is iron. The planet's core is molten metal. And on the surface, iron rules. 95% of all metal is iron and steel. From nails to bridges, from paper clips to skyscrapers, iron holds the world together. Without iron, humanity would collapse back to the Stone Age. No machines, no electricity, no internet. Everything's built on iron. From fiery rivers of molten pig iron in blast furnaces to steel beams holding up skyscrapers, iron is the foundation, the base, civilization's skeleton. Metal of the gods that became metal of the masses. The most abundant, most important, most irreplaceable. Iron, the metal that holds the planet together. The metal that protects all other metals from rust. Picture this: 70% of the world's steel is covered with a thin layer of zinc. Bridges, skyscrapers, cars, ships. Everywhere, zinc stands guard, taking the hit from corrosion. Every second, the world produces 1.5 tons of zinc, 14 million tons per year. It's the fourth largest metal by production volume on the planet, after iron, aluminum, and copper. But they extract it unusually. Zinc is vaporized at 1,800 degrees Fahrenheit, and the vapor is collected. Yes, the metal turns into gas. How do they turn gray ore, mined a mile underground, into a bluish-silver metal that sacrifices itself for others? You'll learn why the ore burns in furnaces, how they collect metallic vapor, and why without zinc, the entire infrastructure of the planet would collapse. Watch till the end. The finale will show what's behind every galvanized beam. This is the story of the bodyguard metal that took on the corrosion of the entire world. A mile underground, darkness, explosion, tons of rock crash down. This is a zinc mine, one of hundreds around the world where ore for the guardian metal is extracted every day. Underground dump trucks with 50-ton capacity haul ore to the mine shaft. An elevator the size of a house lifts the rock to the surface. The ore is dark, almost black. This is sphalerite, zinc sulfide. Crystals with diamond-like brilliance, but the metal content is only 10 to 15%. The rest is waste rock. Trucks carry the ore to the processing plant. The transformation from stone to metal begins. Massive cone crushers as tall as a 3-story building grind ore chunks the size of cars. The noise is deafening. The rock is crushed into gravel the size of fists. Then the gravel goes into ball mills, rotating steel drums 16 feet in diameter, filled with steel balls the size of watermelons. The drum rotates, balls fall, grinding the ore into fine powder. After 8 hours of grinding, you get gray dust, particles the size of sand grains. The ore powder is mixed with water, creating gray liquid slurry called pulp. It's pumped into huge flotation machines, tanks with volumes of 3,500 cubic feet. Chemical reagents are added, foaming agents and collectors. Mixers are turned on and air is fed from below. The magic of flotation begins. Millions of air bubbles rise through the pulp. Particles of sphalerite, zinc ore, stick to the bubbles and float up. A gray foam forms on the surface, 20 inches thick. This foam contains zinc. Waste rock settles to the bottom and is drained off. The foam is collected, filtered, dried. The result is concentrate, powder containing 50 to 60% zinc. From 100 tons of ore, you get 10 to 15 tons of concentrate. This concentrate is loaded into rail cars and shipped to the smelting plant. There begins the real alchemy, turning powder into molten metal. And this is a process where metal turns into vapor. At the plant, concentrate is loaded into fluid bed roasters, massive steel cylinders 66 feet tall. Hot air under pressure is blown in from below. The concentrate powder lifts up, floating in the air like dust. Gas burners are ignited. Temperature rises to 1,650 degrees Fahrenheit. The zinc sulfide ignites. Yes, the ore burns. Sulfur oxidizes, releasing enormous amounts of heat. Sulfur gas flies up the stacks. It will be captured and turned into sulfuric acid. And zinc sulfide transforms into zinc oxide, a gray-white powder. The temperature in the furnace is so high that the walls glow red. The roasted concentrate, zinc oxide, is cooled and mixed with coke, crushed coal. The proportion, 3 parts oxide to 1 part coke. This mixture is loaded into vertical retort furnaces, steel towers 50 feet tall, lined inside with refractory silicon carbide. Heating begins. Temperature starts climbing. 1,800 degrees, 2,000 degrees, 2,200 degrees. At 2,200 degrees Fahrenheit, carbon begins taking oxygen away from zinc oxide. A reduction reaction occurs. But something amazing happens. Zinc doesn't melt. Its boiling point is only 1,665 degrees, but the furnace is at 2,200. So zinc immediately turns into vapor, metallic vapor. Inside the furnace, atoms of gaseous zinc are flying around. The vapors rise up and exit the furnace through piping. They enter a condenser, a special cooled chamber. Temperature in the condenser is around 840 degrees, below boiling point but above melting point of zinc. The vapors condense. Drops of molten zinc settle on the condenser walls, glowing orange. Liquid metal flows down the walls and collects in a receiver. This is crude zinc, contains impurities of lead, cadmium, iron. Purity around 98%. Each furnace produces up to 100 tons of zinc per day. The metal is cast into molds. The result is ingold bars weighing 55 pounds each, silver gray with a bluish tint. For some applications, pure zinc is needed. Then it's refined, purified by distillation. Crude zinc is heated to boiling in a vacuum furnace. Under reduced pressure, boiling point drops to 1,300 degrees. Zinc vaporizes while impurities remain solid. Zinc vapors are condensed in a cooler. The result is refined zinc with 99.99% purity. This zinc is cast into ingots. On the ingot surfaces, a characteristic pattern forms, crystalline designs resembling frost flowers on glass. This is called zinc flowers. Ingots are stacked. Zinc is ready for use, but its main application awaits in hot-dip galvanizing baths. There, steel products will receive corrosion protection. The process looks impressive, like baptism of metal by fire. A steel beam 40 feet long is immersed in a bath of molten zinc. Temperature 840 degrees. The beam completely disappears in the silvery liquid. Chemical reaction begins instantly. Zinc reacts with iron on the steel surface, forming a layer of intermetallic compounds, a solid alloy of zinc and iron. This layer bonds permanently to the steel. On top, a layer of pure liquid zinc. The beam is held in the bath for 1 to 2 minutes. Then it's pulled out. Excess molten zinc drains back. In air, the coating quickly solidifies. The surface becomes silvery, matte, with the characteristic pattern of crystals, zinc flowers. Coating thickness from 2 to 8 thousandths of an inch. That's just fractions of an inch, but it's enough. The galvanized beam won't rust for 50 to 70 years. Even scratches aren't scary. Zinc continues protecting. It's about electrochemistry. Zinc is more active than iron. When corrosion begins, zinc oxidizes, not steel. Zinc sacrifices itself, protecting iron. This is called cathodic protection. World production of galvanized steel, 55 million tons annually. This uses 6 million tons of zinc. Without zinc, modern cities would be impossible. 70% of zinc goes to protecting steel. But there are other applications. Brass, an alloy of copper and zinc, has been known for thousands of years. Contains 15 to 45% zinc. Golden, strong, easily worked. Brass is used for plumbing fixtures, musical instruments, cartridge cases, decorative items. Zinc die casting, a method for manufacturing complex parts for automotives and electronics. Molten zinc is injected under pressure into steel molds. The result is complex-shaped parts accurate to tenths of thousands of an inch. Zinc batteries, still used by the billions. Zinc powder in chemical industry. Zinc oxide in rubber industry, cosmetics, medicine. Zinc ointment heals wounds. World zinc mining, 14 million tons per year. China produces 40%, 5.5 million tons. Peru, Australia, USA, India, other major producers. Zinc price, around $3,000 per ton. The history of zinc as a separate metal began late. Europeans knew brass since ancient Rome, but couldn't obtain pure zinc. The problem, zinc evaporates when heated. Indian and Chinese metallurgists in the 16th century learned to condense zinc vapors in closed retorts. In Europe, pure zinc was obtained by German chemist Andreas Markgraf in 1746, but mass production began in the 19th century. Revolution happened in 1836 when French engineer Stanislas Sorel discovered the hot galvanizing process. He found that immersing steel in molten zinc protects from corrosion. This changed construction forever. Before galvanizing, steel structures rusted within years. With galvanizing, they served for decades. The Eiffel Tower is painted, but many bridges from that era are galvanized and still standing. Today, without galvanized steel, skyscrapers, bridges, power lines, ships are impossible. Zinc, the invisible guardian of infrastructure.
And so, having traveled from explosions a mile deep through giant crushers and flotation tanks, through fluid bed furnaces at 1,650 degrees and retort towers at 2,200, Through transformation into metallic vapor and condensation, zinc emerges, the bodyguard metal of modern civilization. The silvery metal that sacrifices itself, protecting steel from rust. The fourth largest metal by production on the planet, without which all infrastructure would collapse. Every time you see a steel bridge beam, a roofing sheet, or a car body, know they're protected by a thin layer of zinc as thick as a human hair. A layer that takes on corrosion, oxidizes instead of steel, slowly destroys itself, saving the structure. This is a story of nobility at the atomic level, how one metal protects another, sacrificing itself. From underground explosions to silvery skyscraper beams, zinc's journey spans several weeks and 2,200 degrees. The metal that vaporizes to protect, that oxidizes so others don't rust. The invisible shield of 14 million tons annually, standing between steel and corrosion. Zinc. This is why bridges don't collapse, roofs don't leak, and cars don't turn to dust in 5 years. The guardian metal, the sacrificial metal, the metal without which the modern world would simply fall apart from rust.
Every second, 441 nuclear reactors worldwide generate electricity for 1 billion people. But here's what keeps engineers awake at night. Each reactor core operates at temperatures reaching 3,600 degrees Fahrenheit, hot enough to melt concrete, vaporize water instantly, and turn steel into liquid. The only barrier between civilization and nuclear catastrophe is a single steel vessel forged from a 600-ton ingot without a single weld. Picture the weight of 4 blue whales compressed into one seamless cylinder, standing guard over controlled atomic fire. How does humanity forge the largest single-piece objects ever created? How do engineers ensure steel survives conditions that would liquefy most metals? Stick around till the end. You'll discover why only one company on Earth can manufacture these reactor vessels, the jaw-dropping reason welds are forbidden, and the shocking truth about what happens when forging goes wrong at the atomic scale. The story begins at Japan Steel Works in Muran, Japan, the only facility worldwide capable of forging complete reactor pressure vessels from single steel ingots. This monopoly isn't marketing, it's physics. Their forging press, standing 12 stories tall and weighing 14,000 tons, generates forces equivalent to stacking 70 statues of liberty on a dinner plate. That's the mechanical advantage required to shape 600 tons of glowing steel. The facility consumes enough electricity to power 25,000 homes during forging operations. Backup generators the size of locomotive engines ensure power never interrupts mid-forge. A single unexpected cooling would create internal stresses shattering the vessel like glass. The plant operates 3 shifts daily, yet completes only 4 reactor vessels annually. Each vessel requires 8 months from raw steel to finished product. That's longer than human pregnancy, applied to metalworking requiring tolerances measured in thousands of inches across objects 30 feet tall. Next comes steel creation, where metallurgists blend iron with precise amounts of manganese, nickel, chromium, molybdenum, elements chosen for neutron resistance and high temperature strength. The recipe, classified by nuclear regulatory agencies, creates alloy capable of withstanding 50 years of continuous neutron bombardment without becoming brittle. Standard steel exposed to reactor conditions becomes fragile within months. Reactor-grade steel must maintain ductility for half a century. Electric arc furnaces, consuming megawatts of power, melt 300 tons of scrap and alloys at 3,000 degrees Fahrenheit. Molten steel flows into massive ladles lined with refractory bricks capable of containing liquid metal without dissolving. Workers add deoxidizers and desulfurizers, removing impurities at parts per million levels. Even microscopic inclusions, trapped oxides, sulfides, or air bubbles become crack initiation sites under reactor pressures exceeding 2,200 pounds per square inch. That's pressure crushing car engines like soda cans. Giant molds assembled from water-cooled copper plates standing 20 feet tall receive the molten pour. Liquid steel enters from bottom up through ceramic pipes, filling the mold cavity in controlled flow, taking 40 minutes. Technicians monitor fill rates continuously. Turbulence during pouring traps gas bubbles, creating voids. After filling, the ingot, now a glowing cylinder weighing 600 tons, solidifies over 72 hours under computer-controlled cooling. This cooling phase determines everything. Cool too fast, thermal stresses create internal cracks invisible to naked eyes but catastrophic under reactor operation. Cool too slow, large crystals form, weakening the structure. Thermocouples embedded throughout the mold measure temperature at 300 points simultaneously. The ingot shrinks 5 inches in diameter while cooling, enough movement to crack the mold if thermal expansion isn't calculated precisely. Workers strip the mold after 3 days, revealing a steel cylinder glowing dull red at 800 degrees. Now comes forging, the ancient art of shaping hot metal, scaled to industrial extremes. The 600-ton ingot, reheated to 2,300 degrees Fahrenheit in furnaces large as houses, glows brilliant orange. At these temperatures, steel becomes plastic, not liquid, but deformable under immense pressure. Picture clay that weighs as much as a jumbo jet. Overhead cranes operating at weight limits requiring structural reinforcement throughout the building lift the glowing ingot onto the press bed. The press ram, a solid steel cylinder 6 feet in diameter, descends with force exceeding 14,000 tons. That's pressure equivalent to balancing 30 fully loaded Boeing 747s on a car hood. Under this incomprehensible force, 600 tons of steel deforms, spreading like bread dough, forming into a thick-walled cylinder. Each press cycle compresses the ingot 3 inches, then retracts. The process repeats hundreds of times over weeks. The forging process requires balletic precision at colossal scale. After each press cycle, massive manipulators rotate the workpiece 7 degrees. Computer systems track rotation angle to within 0.1 degrees. Because uneven forging creates thickness variations leading to stress concentration, the ingot must be reshaped uniformly, ensuring wall thickness varies less than 1% across the entire vessel. This step is critical because reactor vessel integrity depends on grain structure. Each press cycle compresses and elongates metal crystals, aligning them perpendicular to stress directions. This crystallographic texture increases strength 30% over cast steel. Between press cycles, the workpiece returns to furnaces for reheating. Temperature drops to 1,800 degrees during forging, making steel too stiff to deform further. The ingot cycles between press and furnace 60 times, spending cumulative hours at extreme temperatures requiring constant atmospheric monitoring to prevent oxidation. After rough forging establishes basic geometry, precision machining begins. The forged cylinder, now weighing 450 tons after material redistribution, moves to vertical lathes with cutting surfaces 20 feet in diameter. Carbide tools, costing thousands of dollars and lasting mere hours, remove steel and continuous spiral cuts. Metal shavings, glowing red from friction heat, pile like metallic spaghetti. Picture this. Machinists target wall thickness of 8.7 inches with tolerance of plus or minus 0.05 inches. That's maintaining consistency thinner than a penny across surfaces 40 feet in circumference. Ultrasonic sensors scan continuously, creating 3-dimensional maps of wall thickness. Any thin spot becomes pressure concentration point, and at 2,200 psi operating pressure, stress concentrations cause catastrophic rupture. Modern reactors operate at pressures where even microscopic flaws propagate into fractures within microseconds once initiated. Quality control transcends normal manufacturing standards, entering realm of nuclear safety protocol. Ultrasonic inspection systems, using sound waves at frequencies beyond human hearing, detect internal flaws smaller than grains of rice. Technicians scan every cubic inch of the 450-ton vessel, searching for voids, inclusions, or crystal boundary irregularities. This inspection process alone takes 6 weeks of round-the-clock work. Next comes stress relief heat treatment at 1,100 degrees for 48 hours. This annealing process allows internal stresses from forging to dissipate through autolytic diffusion. Without stress relief, residual tensions from manufacturing cause cracks years later during operation. After heat treatment, hydrostatic pressure testing subjects the vessel to 3,300 psi, 50% beyond operating pressure. Workers flood the interior with water, then pump pressure until the vessel expands measurably. Any weakness reveals itself through leakage or deformation. Passing this test certifies the vessel can contain reactor core meltdown scenarios. This wasn't always possible. Back in 1955, early reactor vessels used welded construction, multiple curved plates joined by fusion welding. The Windscale reactor fire in Britain that year released radioactive iodine when welded seams failed under thermal stress. Investigation revealed welds created heat-affected zones where crystal structure changed, becoming brittle under neutron bombardment. The breakthrough came when Robert Withrich at Combustion Engineering proposed seamless forging in 1963. However, no forge press existed powerful enough. Japan Steel Works developed their 14,000-ton press in 1967 specifically for reactor vessels, recognizing the strategic importance. By 1975, all new reactor designs mandated seamless forgings. Today, the safety record speaks volumes. Zero pressure vessel failures in commercial reactors using forged construction. The few accidents that occurred, 3 Mile Island, Chernobyl, and Fukushima, involved cooling system failures, not vessel integrity. Those forged steel shells contain disaster, preventing far worse outcomes. Carbon emissions avoid 48 billion tons annually through nuclear power generation versus coal, equivalent to removing every car, truck, and plane from operation for 3 years. Nuclear energy costs drop 62% per kilowatt-hour versus solar with battery storage. A single reactor vessel forged today will generate electricity for 80 years, powering 3 million homes throughout its lifetime. So here's the secret promised. These vessels can't be welded because neutron radiation does something insidious to metal. It transmutes atoms. High-energy neutrons knock atoms from crystal lattice positions, creating vacancies and defects. Over decades, accumulated damage makes steel brittle. Welds, where crystal structures merge imperfectly, accumulate damage faster. The heat-affected zone becomes embrittlement accelerator. Seamless forging eliminates this Achilles heel entirely. Every atom in the vessel exists within continuous crystal structures aligned through forging. There are no boundaries to fail, no weak points to fracture. From 600-ton ingots to civilization's guardians, cycle completes. We've engineered the ultimate containment, steel vessels standing between humanity and atomic fire for generations. These aren't just industrial products, they're monuments to engineering paranoia in the best sense, over-engineering driven by understanding that failure means catastrophe. That forged steel cylinder represents humanity's ability to harness cosmic forces while building redundant safety margins into physical structures. We've learned to respect the atom's power by building cages worthy of containing it.
Without nickel, Tesla's electric vehicles wouldn't exist. Every year, over 3 million tons of this silvery metal get extracted from Earth's crust, 70% destined for stainless steel, 30% powering the battery revolution transforming transportation. Picture this. Inside every electric car battery, nickel accounts for up to 80% of cathode weight, storing the electrical energy making 500-mile ranges possible. How does rock buried 2 miles underground become the metal enabling carbon-free futures? How do ancient asteroid impacts create deposits worth billions? Stick around till the end. You'll discover why this metal, discovered in 1751, became overnight the most critical resource for climate solutions, and the shocking environmental price we pay for every kilowatt-hour stored. The story begins in Sudbury, Canada, ground zero for one of Earth's largest meteorite impacts. 2 billion years ago, a 6-mile-wide asteroid slammed into primordial crust with force equaling 6 billion Hiroshima bombs. That cataclysmic collision melted rock 60 miles deep, concentrating nickel-rich magma into deposits mining companies extract today. Standing at crater's edge feels like visiting Earth's wound that never healed. Modern mining descends through vertical shafts, plunging 7,000 feet, deeper than 6 Empire State Buildings stacked vertically. Massive cage elevators, traveling at speeds exceeding 30 miles per hour, drop miners into darkness in under 4 minutes. That's falling through bedrock older than complex life itself. Underground, temperatures reach 120 degrees Fahrenheit from Earth's geothermal heat, requiring industrial air conditioning, pumping cold air through 40-mile tunnel networks. Next comes extraction, where explosive specialists drill blast holes following nickel-bearing veins. Charges containing ammonium nitrate, industrial explosive used in quantities measured by tons, fracture solid rock with controlled violence. The deafening thunder from underground blasts shakes surface buildings miles away, rattling windows in synchronized waves every afternoon at precisely 4 o'clock shift change. Giant load haul dump machines, nicknamed LHDs, and standing tall as double-decker buses, scoop 50 tons per bucket. Picture mechanical mastodons navigating tunnels barely wider than their frames. Operating in perpetual darkness, illuminated only by headlamps, drivers maneuver 60-ton machines through labyrinths where wrong turns mean hours backtracking. Every shift, these machines transport 15,000 tons of ore, weight equivalent to 75 blue whales, through underground highways to crushing stations. Surface processing begins where jaw crushers, standing 4 stories tall with opening widths matching garage doors, pulverize boulders into gravel-sized chunks. With bone-rattling vibrations felt through steel-toed boots, hydraulic jaws generate crushing forces exceeding 15,000 pounds per square inch. Operators monitor crack propagation. Rocks splitting wrong create jams requiring dangerous manual intervention with jackhammers. Conveyor systems stretching 8 miles, longer than Central Park, transport crushed ore to grinding mills. Inside rotating drums 30 feet in diameter, 25-ton steel rods tumble with ore, creating grinding cacophony resembling continuous thunder. Processing 12,000 tons hourly, that's loading freight trains non-stop. This powder, finer than beach sand, flows to flotation cells, where chemicals separate nickel sulfides from waste rock using bubble physics. Nickel concentrate emerges containing 20% metal, ready for the real challenge: purification. Next comes roasting, a pyrometallurgical inferno where concentrate gets heated in massive kilns to 1,400 degrees Fahrenheit. At these temperatures, sulfur burns away as sulfur dioxide, leaving behind nickel oxide mixed with iron. Picture industrial-scale barbecuing where the meat is rock and smoke contains compounds requiring scrubbing before atmospheric release. The roasted material, now crumbly and porous like volcanic pumice, moves to smelting furnaces, where temperatures climb to 2,600 degrees Fahrenheit. Electric arc furnaces, consuming power equivalent to small cities, enough electricity to run 12,000 homes, melt oxide into liquid matte. This molten mixture, containing 60% nickel and 40% other metals, glows white-hot like captured starlight. Every 2 hours, furnaces tap this liquid fire into ladles holding 200 tons. The purification process intensifies with converting, where oxygen blasted through molten matte at supersonic speeds burns away remaining sulfur and iron. Massive Peirce-Smith converters, rotating horizontal cylinders 40 feet long, operate like blast furnaces lying sideways. Inside these rotating drums, chemical warfare occurs. Oxygen attacking sulfur bonds, creating temperatures hot enough to vaporize copper. This step is critical because timing determines purity. Blow too long, nickel oxidizes wastefully. Too short, impurities contaminate final product. Operators monitor color changes in flames shooting from converter mouths. Blue flames mean sulfur burning, yellow indicates iron removal, clear white signals nickel ready. That visual chemistry, unchanged for centuries, guides decisions affecting millions in product value. After converting, nickel matte achieves 78% purity, but battery manufacturers demand 99.9%. After converting, the real magic begins, electro-refining. Here, physics and chemistry converge in massive electrode halls housing thousands of cells. Impure nickel anodes, cast into plates weighing 300 pounds each, suspend in electrolyte baths containing nickel sulfate and sulfuric acid. Electric current flowing through these baths, think industrial-scale electroplating, dissolves nickel atoms from anodes, transporting them through liquid to deposit on pure nickel starter cathodes. Picture this: over 10 days, nickel migrates atom by atom across 6-inch gaps. Impurities like cobalt, copper, iron stay behind, falling as sludge to cell bottoms. This sludge, later processed separately, contains precious metals including platinum, gold, palladium, making waste worth more than many ores. Temperature control matters critically. Too hot, dendrites form, metal crystals bridging electrodes causing shorts. Too cold, deposition slows uneconomically. Electro-refining requires surgical precision in industrial setting. Computer systems monitor voltage, amperage, temperature across 15,000 individual cells simultaneously. Operators adjust current by milliamps. Modern refineries achieve nickel purity of 99.99%, only one impurity atom per 10,000. That's purity rivaling semiconductor-grade silicon. After 10 days, workers crane lift finished cathodes, now coated with 400-pound nickel deposits from baths. Mechanical strippers peel nickel from starter sheets like removing wallpaper. These pure nickel sheets, called cathodes, get melted into pellets for battery manufacturers, or alloyed with chromium and iron for stainless steel. The energy intensity staggers. Producing 1 ton of battery-grade nickel consumes 50 megawatt-hours, enough electricity to power average American homes for 60 days. This industry transformed radically in 15 years. Back in 2010, nickel prices averaged $7 per pound, used primarily for stainless steel. Battery applications consumed less than 5% of global production. That all changed when Elon Musk's Master Plan 2 announced Tesla's battery gigafactories in 2016. The breakthrough came when battery chemistry shifted from cobalt-heavy NCAs to nickel-rich NCMs, nickel, cobalt, manganese cathodes containing 80% nickel. Suddenly, every electric vehicle needed 110 pounds of nickel. Global demand exploded. Prices spiked to $9 per pound by 2022. Indonesia, containing 21% of world's reserves, transformed from minor player to dominant producer. Today, battery applications consume 43% of new nickel production. By 2035, International Energy Agency projects batteries will consume 75%, driven by 200 million electric vehicles requiring 23 million tons cumulatively. Carbon emissions drop by 18% when recycling nickel versus mining virgin ore, equivalent to removing 3 million cars annually. Industry saves over $22 billion yearly through recycling. Processing costs drop 31% because smelting scrap requires half the energy of complete ore processing. So here's the secret promised. Nickel is humanity's transition metal, literally bridging fossil fuel era to electric future. But here's the dark truth. Extracting nickel for just one EV battery produces 8 tons of CO2 emissions. That electric car carries invisible environmental debt, requiring 35,000 miles of driving before breaking even with efficient gasoline vehicles. The green revolution isn't free. It's an energy trade-off where extraction today enables emission reductions tomorrow. From asteroid impacts to electric highways, cycle completes. We're mining ancient cosmic collisions to power climate solutions. Nickel doesn't solve pollution, it relocates it, concentrates it, transforms it into manageable problem. That's not failure, that's engineering reality. Every solution creates new challenges. The question isn't whether mining nickel harms Earth, it does. The question is whether preventing catastrophic climate change justifies temporary scars.
Every year, the world cranks out over 100 million cubic meters of medium-density fiberboard. That's such a massive amount that you could build a road around the entire planet with it, every single year. Imagine this. What was once trash, sawdust, wood chips, and scrap paper, is now transformed into a material worth over $25 billion. China controls half of the entire volume, while Europe and the US add millions of cubic meters each year. But what's really going on behind the factory walls, where wood dust goes from being waste to perfectly smooth panels? If you stick around to the end, you'll learn a secret that's usually kept hidden. The foundation for medium-density fiberboard isn't whole logs, but what used to be considered rubbish: sawdust, wood chips, offcuts, and even old scrap paper. It's a triumph of smart resource use. These mountains of wood waste are brought to the plant and first get a thorough cleaning. Powerful magnets pull out any metal contaminants, nails, staples, while screening systems remove sand and stones that could damage the expensive equipment. After that, the raw material goes into a huge vat where it's washed and steamed with hot steam. This isn't for cleanliness. It's done to soften the lignin, the natural glue that holds the wood fibers together. Now comes the most important step, the one that separates medium-density fiberboard from its rougher cousin, particle board. The prepared, softened wood chips are fed into a machine called a defibrator, or refiner. Imagine two giant metal plates, like millstones, spinning towards each other at enormous speed. On their surfaces is a complex pattern of sharp ridges and grooves. The wood mass gets caught between these discs, and they literally comb it apart into its tiniest components, tearing it into individual wood fibers. This isn't shavings anymore. It's something like a fluffy, moist cotton, or wood flour. We've just deconstructed the wood down to its basic building blocks. Next, this fibrous mass needs to be dried. But it has to be done very quickly, before the fibers start to stick together. So, they're blown into a long, hot tube dryer. A stream of hot air picks up the fibers, and as they fly through this tube, all the excess moisture evaporates from them. And right here, while the fibers are still hot and flying in this whirlwind, the next key stage happens: resination. A fine mist of a binding agent is sprayed into the airstream through special nozzles. This is urea resin, our glue. This mist envelops every tiny fiber, coating it with a thin, sticky film. It's a very efficient method that guarantees a perfectly even distribution of the glue. Now this resin-soaked, dry, and light as fluff mass is ready to become a board. It goes into a forming machine. The stream of fibers settles onto a wide, moving conveyor, forming a thick, fluffy, and perfectly uniform mat. Special rollers slightly compact it, and giant knives cut off pieces of the required length. It's already starting to look like a future board, but for now, it's just a thick, soft mattress of wood fluff. And now comes the climax: hot pressing. This fluffy mat rolls into a giant press. This can be either a multi-opening press that squeezes a whole stack of boards at once, or a continuous press that looks like giant moving tracks. And here, our mat is hit by two powerful forces at the same time. First, colossal pressure. The press plates squeeze our fluffy mattress with hundreds of tons of force, reducing its thickness several times and squeezing out all the air. The wood fibers are pressed tightly against each other, forming an incredibly dense structure. Second, a high temperature of 400 degrees Fahrenheit. That's 200 Celsius. This heat does two things. It activates the resin, causing it to polymerize and permanently glue the fibers into a single solid block. And at the same time, it evaporates any remaining moisture, which escapes from the board as hissing steam. After a few minutes in this steel embrace, the fluffy mat transforms into a hard, dense, perfectly flat, and still very hot board of medium density fiberboard. After the press, the hot boards can't just be stacked. They need to be cooled to relieve internal stresses. They're placed in a special fan cooler, which looks like a giant filing cabinet, where they slowly cool while being fanned with air. Once the boards have cooled, it's time to give them a finished look. First, they're stacked in high piles and left to rest for a few days. This stabilizes their internal structure. Then, each board goes through a sanding machine. Imagine a giant belt sander with several heads. Wide abrasive belts remove a thin surface layer from both sides, bringing the board to a perfectly precise thickness, for example, 16 or 18 millimeters, and creating that famous smooth as paper surface. And the final touch, cutting. Huge saws cut the large industrial boards into standard commercial formats. After this, each batch goes through strict quality control. Its density, strength, thickness, and surface quality are checked. The finished, perfectly smooth boards are labeled, packaged, and sent to furniture factories, where they will become the foundation for elegant and stylish items in our homes, silently demonstrating the noble path that ordinary wood dust can travel. The global market for medium-density fiberboard is a giant machine that turns over more than $25 billion a year. And this machine has no plans of stopping. Forecasts say it will grow by 6% every year. That means the demand for this smooth material is just insane. So who's the head chef in this kitchen? The undisputed king is China. It produces over 50% of all the medium-density fiberboard in the world. But Europe is no slouch either, with powerful players like Germany, Poland, and Turkey producing millions of cubic meters of high-quality board. Now for the volume. Every year, about 100 million cubic meters of medium-density fiberboard are produced worldwide. That number is so huge, it's impossible to imagine. Let's try. Picture a road. If you took all that medium-density fiberboard and built a road 10 meters wide and 25 centimeters thick, you could wrap that road around our entire planet at the equator every single year. It's an endless stream of material being turned into furniture, doors, and panels for our homes. Every year, the world melts over 1 billion tons of pig iron. But where does all that fiery metal come from? Imagine a giant furnace as tall as a 35-story skyscraper that never sleeps. Its guts glow like the Earth's core, and the temperature hits 3,600 degrees Fahrenheit. That's 2,000 Celsius. This is a blast furnace. They don't just melt metal here. They give birth to the heart of industry. But there's a secret that only the guys standing at the tap hole know. If you stick around to the end, you'll find out what's really happening in the center of this burning fortress, and why it changes everything. Imagine a colossal tower, taller than a 35-story skyscraper. The ground beneath your feet vibrates slightly from its relentless work, and the air is filled with a hum, like the breathing of a giant beast. At night, its top glows, pushing back the darkness. This is a blast furnace, a massive vertical smelter, where 24 hours a day, 7 days a week, the magic of turning ore into metal happens non-stop. Why blast furnace? The name comes from the process itself, and it's no accident. The whole secret to a blast furnace is the constant blast of incredibly hot air that fuels the fire and kicks off all the necessary reactions. If you were to slice a blast furnace open, you'd see it looks like a stretched out bottle. Every part of it has a name and a purpose. The walls of the furnace are lined with special refractory bricks, capable of withstanding temperatures that would melt solid rock. This is a true fortress, built to tame fire itself. So what do they feed into this fiery throat? The process is like cooking from a very strict recipe. The mix of ingredients loaded into the furnace is called the charge. Here are its main components: iron ore, fuel, coke, and fluxes. These three ingredients are loaded into the furnace in precisely measured layers. A layer of coke, then a layer of ore with fluxes, then coke again, and so on. Every few minutes, a new batch weighing tens of tons is sent into the furnace. The iron ore is the foundation of it all. They usually don't just use raw ore dug from the ground, but specially prepared sinter or pellets. These are baked clumps of fine ore, or rolled balls of ore concentrate. The main goal is to have as much iron oxide in the raw material as possible, from which the oxygen will later be ripped out. Coke is coal that's been cooked in special ovens without access to air. After this treatment, it becomes strong, porous, and burns with an immense amount of heat. But that's not its only role. The carbon that makes up coke is the real magician that turns ore into metal. The flux is most often ordinary limestone. Why is it needed? The ore and coke always have useless impurities, so-called gangue. The limestone helps to bind these impurities, forming an easily meltable slag. So, the charge is loaded. What's next? This is where it gets interesting. Two streams move towards each other. From the top, the layers of the charge slowly descend, and from the bottom, a hurricane of superheated gases rushes up to meet them. It all starts at the bottom, in the hearth. Through special pipes called tuyères, air heated to a scorching 2,200 degrees. Fahrenheit, 1 to 200 Celsius, is blasted into the furnace under huge pressure. That's hotter than volcanic lava. Meeting the red-hot coke, the oxygen in the air instantly ignites. The temperature in this zone skyrockets to 3,600 degrees Fahrenheit, 2,000 Celsius. This creates carbon dioxide. But as it rises higher and passes through new layers of coke, it turns into another gas, carbon monoxide. And this gas is the real oxygen thief. As this searing hot stream of gas rises up the furnace shaft, it envelops the chunks of ore and begins to greedily rip the oxygen from them, leaving behind reduced, spongy iron. The reduced iron continues its journey downward into hotter and hotter zones. It passes through the glowing layers of coke and, like a sponge, begins to soak up its carbon. And here's where something amazing happens. Pure iron melts at a very high temperature of 2,800 calories, 1,530 nanometers. But soaking up carbon dramatically lowers that melting point. That's why a blast furnace doesn't produce pure iron, but an alloy of iron and carbon, pig iron, which becomes liquid at just 2,200 nanometers, 1/200 nanometers. Roughly every 40 to 60 minutes, enough liquid products have collected in the bottom of the furnace. It's time for the climax, a truly mesmerizing sight. A furnace worker, the keeper, uses a special drill to punch open a hole in the furnace wall, the tap hole. First, they tap the slag. It's lighter than the iron, so it floats on top. It's a molten, lava-like mass that flows into special ladles. And then they open the iron tap hole, and a dazzling, sparking stream of molten metal erupts with a roar. This is the river of fire. The temperature of this stream is around 2,700 degrees Fahrenheit, 1,500 Celsius. It flows down special troughs, bathing everything around in a blinding light, and fills giant ladles that look like railway tankers. Each of these ladles holds hundreds of tons of liquid metal. From here, the pig iron will be sent to its next stage, either poured into molds or, more often, sent for further processing into steel. A blast furnace is an amazing operation that produces more than just pig iron. The byproducts are just as important. The blast furnace slag, which we've already mentioned, becomes a valuable raw material for making cement, building blocks, and road aggregate after it's cooled and crushed. The blast furnace gas that comes out of the furnace isn't just released into the atmosphere. It's cleaned of dust and used as fuel to heat the very same air that's blasted back into the furnace. It's a closed-loop system that makes the process more economical. Without a doubt, metallurgy is a serious challenge for the environment. However, modern technologies are constantly evolving. When blast furnaces are modernized, powerful filters and cleaning systems are installed to capture dust and harmful gases. Scientists and engineers around the world are working on creating green technologies, like using hydrogen instead of coke, to make metal production cleaner. But for now, the blast furnace remains the king of metallurgy. And every time you see a bridge, a skyscraper, or a train, remember these fiery giants and the people who tame rivers of fire to give the world a strong and reliable foundation. For 75 years, from the late 19th century to the 1970s, the USA was the undisputed world leader in the production of pig iron, steel, and rolled products. During this period, the American iron and steel industry wasn't just a sector of the economy, it was the key, or barometer, of the American economy. In the 1920s, for example, the country produced about half of the world's pig iron. Imagine that. Every other ton of this strategic metal in the world was born right here in American furnaces.